Three Rivers Physics people, Professor Martineau here. And last week I tried to do a demonstration from charge induction because I figured which student had a really good question about how can neutral objects actually have charged characteristics? Or why is it that charged objects or neutral objects get attracted to charged objects? And I did explain it a little bit and I had a demonstration, but the video was too far away. And so what I said was, well, I'll do a full-on video. I'll load it up to my YouTube channel, and then I'll give you the link to it. So this is a redo of that. I'm going to reference this video in our lecture tonight because I'm not going to sit with you and watch it because you're grown-ups. But I do really suggest you watch it. Well, you're watching it right now, but I will suggest that you watch it because I'm not going to do this live in class because I'm doing it right here. Anyway. So let's go over charging again. So if an object is net charge, has a net charge to it, it means it has more of one type of charge than another. So it has more electrons than protons. Again, realize that you cannot add protons to a charge, to any object, because that would be stripping them out of the nucleus. That's impossible. So really what you're either doing is something is negatively charged, you're adding electrons onto the object, or if it's positively charged, you're stripping electrons away or off the object, right? And the way they charging objects by stripping electrons is really easy. The electron is really far away from the nucleus, so the amount of Coulomb force that the nucleus can pull on that electron with is very low, and pound for pound, so the electron is very far away from the nucleus of the atom. It's not close at all if you look at it to scale. So one thing we can do is called frictional charging. So what we're going to do is we need an insulator. I mentioned this last time. Right, then an insulator, what an insulator does is it holds on to charge and doesn't flow through the object. So for instance, the styrofoam plate is an insulator. If I deposit charge onto this plate, the charges stay on the plate and don't go anywhere. That's what makes it an insulator. Or if I pull charges off this plate, it'll stay charged. A conductor, you can put charges on a conductor, but those charges that end up on that conductor go right through the conductor onto the next available conductor and go right into the ground. So I'm a conductor, this is an insulator. So if I charge this insulator, the charges will stay on the insulator, not run through me into the ground. Again, negative charges want to seek the ground, the physical ground of the earth, right? So that's just one of their characteristics. If I had a piece of metal and I tried to charge it, I'd charge it, but eventually what would happen is those charges just kind of go off of me and into the ground, so it doesn't really matter. So the styrofoam is an insulator. What I need is something else that will strip the charges off of that, and a classic way to do that is with this, yes, authentic bunny fur. Now, before I get any calls from the ASPCA, right?
Yeah.
All right. This is older than me. This comes little bits of fur flying off of it. We've had this in my high school since before I was there, and I've been there for 21 years. So this rabbit is long since gone, and even if it didn't if it met a premature death, I had nothing to do with it, and it was probably before I was born. This is really old fur. So what I'm going to do is I'm going to charge up the plate with the fur. So right now I have either stripped electrons off of the plate, making it positively charged, and I've deposited those onto the fur, making this negatively charged, or the plate has stripped electrons off of the fur and made this negatively charged and made the fur positively charged. And quite honestly, by looking at it, I can't tell which one that is. Now, there is a chart in the book. You can determine that. I don't know who came up with that chart, but if it says, if you rub amber on fur, it will become negatively charged or something like that. But right now we're going to do pretendy time. So what I'm going to do is I'm going to charge up this plate, and now I'm going to pretend that it's negatively charged just for the sake of argument, right? If I charge up this balloon, so there's a balloon over here, and I charge that up on the plate, then what we should get is that they should be attracted to each other, and they kind of are, but I'll show it better. Well, it's attracted to me.
It's attracted to you.
Certainly, right? Okay, so the bottom line here is I wanted to show the attraction between two like charges, right? But the question was, how can an object that's neutrally charged be attracted to something that's negatively charged? I thought only opposites attract and likes repel. How can neutrals and negatives and opposites, or neutral and negative, be attracted to each other, right? I thought neutral didn't have a charge. Therefore, a neutral object doesn't feel the Coulomb force because it's not charged. Well, there's a reason behind that. So we're going to demonstrate that with the bunny fur again. So we're going to bunny fur this. I tried to show this last time, but these are little ordinary pieces of paper. Okay, they are not charged. Okay, they're not sticking to my hand, right? So they're not electrostatically charged. They are neutral. They have equal amounts of negative charge and positive charge. Once again, just for the sake of argument, we're going to say that when I do this action, I have made this plate negatively charged, just because. Okay, now what we're going to do is we're going to bring the plate in, and we should see the effect. And we should see that. There we go.
I can see it.
I got one. Did you get it?
Yeah.
There we go. Right? It lifted up, and now it's stuck to the plate. So, but these, look at that. These are, but the pieces of paper were negatively charged. What's the deal? Well, the deal is that this plate was definitely negatively charged because I charged it by rubbing. Okay. These pieces of paper became charged by something called charge induction. These pieces of paper are insulators. Okay, or yeah, they're insulators. So they're not going to jump off of those. The charges are going to jump off the piece of paper. But what's going to happen is that the negative and positive charges inside that piece of paper will align themselves with the negatively charged plate. So the positive charges inside the paper get close to the negative charge of the plate. The negative charges in the paper get away from the negative charge of the plate, making these pieces of paper act like they're charged, or there's more of one charge on one side of the paper than the other side of the paper. And when that happens, the positive charges in the paper are attracted to the negative of the plate, and they get attracted to it. So again, the paper is still neutral. It's just that it's behaving as though it's charged because it's aligning all of the charges inside the paper in accordance to the actual charge on the charged plate. And we can do the same thing with the balloon. So might as well just do the balloon while we're here. So I'm gonna rub the balloon. If I had hair, my hair would stick up. I don't. Right, so that comes up real nice. Okay, once again. Again, this piece of paper right here, it's feeling two forces. One is gravity down, and one is the electrostatic force up. And let's think about that. The whole Earth is pulling on that piece of paper. That's where the gravity comes from. And this balloon is pulling up on this paper, and the balloon is winning. So all of the mass of the Earth combined, contributing to the gravitational force on that piece of paper, is not enough to counteract a lot of little charges pulling up on the piece of paper. So electrostatics are far stronger than gravitational forces pound for pound. And just to kind of round it out, we're going to do lastly with another insulator. This is a piece of PVC pipe. Okay, so PVC is a really good insulator of charge. We'll charge that up, and again, we should see the same effect.
Oh, that's so cool.
And it's standing up.
They're standing up.
So that one's dancing.
Oh.
See that? Okay. It's not magic, though. A lot of back in the day, people thought electricity was basically magical because blue sparks magically came out of things. Things floated for no reason, right? So people thought it was negative. Now, one last demonstration we know with this pipe is that we know that the water molecule is electrically neutral. It has equal numbers of electrons and protons on the water molecule. Sorry, but we also know that the water molecule has a very peculiar shape. It looks like a V. It looks like a triangle with the big oxygen here and the two hydrogens on the legs of that water molecule. If you don't know what a water molecule looks like, Google a picture that will classically look like a V. The oxygen molecule has 8 electrons on it. The hydrogens have 1 electron on it, but, am I saying that right? Yeah, I'm saying that right. Yeah, so it doesn't matter. I think I said that right.
Oxygen is atomic number?
It's 8.
8?
Yeah, okay. So
8 and 16,
So the bottom line here is that even though there's equal numbers of not positive and negative charges on the water molecule, because of the arrangement of the atoms in the water molecule, there's more, it's front-loaded with one type of charge on the oxygen side and not as much charge on the hydrogen side. So water becomes a polar molecule. Even though it's electrically neutral, it behaves as though it's electrically charged. It has an induced charge on it. And since water is neutral, but can have an induced charge put on it, let's go check it out. So I'm going to charge up the rod.
Can you touch the metal?
Yeah, it should be fine. If not, I'll just recharge it.
Okay.
We get a stream of water coming out. And what we're going to do is we're going to
Oh, that's neat.
bend. Go from the other side too. Oops, sorry. Let me charge it up one more time. Let that
Okay.
go.
We're just gonna watch the water drip.
Drip, drip, drip.
That is so
Right?
neat.
So the neutral water, even though they're neutral, the polar characteristics of the water molecule makes the charged end of the water molecule, whatever the charge is opposite to the charge on this rod, it's going to get attracted to that, and it bends the path of the water going down. And whenever you see an object change its direction, it's feeling a net force. So that net force is, it's got two forces on it: gravity down, and this thing over to the left. So the net is that way at an angle, right? When you sum those two forces. All right. So lastly, we're going to look at this thing called the electroscope. It's referred to in the book a couple of times, and it might look different, but this is my electroscope. So let's take a look at it. So the electroscope has a metal stand here, okay? That's a conductor. Metal rod here, metal ring here. But these two strings are insulators, so they're very thin.
There you go.
Yeah, they're very thin black strings right here. So these are insulators. And at the end of the insulated strings are two wadded up balls of aluminum foil, which are conductors, which means negative charges will freely flow within the aluminum foil because it's a conductor, right? It moves around very easily. But these two conducting spheres are insulated from the rest of the table, so it is not connected to ground. Otherwise, if a charge were deposited onto that aluminum foil sphere and it were connected to ground, the charge would go into the sphere, up through the string, down through the stand, into the table, into the ground, and then it wouldn't be charged, right? What we want to do is we want to induce a charge on these conductors. So here's how we're going to do it. Rod again, charge it up. Now watch the effect. I'm going to try to do it a couple of times because you know what we're looking for.
Yeah, I'm gonna go this side because I
Okay.
might be able to see it better.
Okay, so what we're gonna do here is we're gonna bring it. What's the matter?
I just want to make sure they're not moving.
Okay, ready?
Yeah.
So we're gonna come in.
Ooh.
No, I'm gonna do that again. You should have seen two different things happen. You should have. I'm gonna do it again before I say what you should have seen happen.
Let me stop them.
Okay, ready? So here, this is the charged rod. I charged it up. Okay, here we come.
Oh, that's the coolest
That's
thing.
really neat. Now it seems like, well, so what? The walls just moved. But let's think about what's happening here, okay? I got the charged rod, so I'm not going to do it again. Right now, the rod's neutral. Basically, if you want to uncharge something, what do? You touch it. Mm-hmm. What happens when you touch it? Any extra charges that are on your charged object are going to go into your hand, through your body, into the ground, and now it's neutral again, right? Okay, so let's look at what's happening. I charge the rod. Let's say that it's negatively charged. I bring it close to the aluminum foil, right? It induces a charge in the foil such that, so if this is negative and I bring this close in, the positive charges in the foil will get attracted to the rod and bring these two in. But then what happens? And you can't hear it, but if you're close, you can hear it. If this gets close enough, once they come in, these two aluminum foil balls will come in. Now they're inducing a charge and they're being attracted to the rod. Once they touch the rod, they're given, and I'm touching the rod, then it's giving a path for the extra negative charges to go through the rod, into my hand, down through the ground. And then what happens after that? The negative charges have been transported off of the aluminum foil balls, through my hand, into the ground. Now both of these balls are positively charged, and then they repel each other and they go out. And if we had it like a really good electroscope, you would see they would just sit here and do this. Like this one is a mess because they fly all over the place. But if you had a really good electroscope, they would come together and then they'd hit the rod and then come out and literally stay like this and kind of like bounce a little bit. right? Because they are now the same charge and therefore are going to repel each other. So let's look at that effect one more time.
So when we use the beaker and do this,
Yep.
and we use the paper clip and just the thin leaf of foil,
Yep.
they stay apart.
Yeah.
Is it because it's just a thin leaf of foil?
Yes.
As opposed to a
This
ball
has-
of foil?
Yeah, well, it's also because the string isn't giving them a lot of.
Oh,
it's
okay.
It's not real sturdy.
Okay.
So let's do it one more time. So we're charging up. Again, we're looking for rods coming in. Rods coming in induces a charge in the ball, which attracts them to the rod. It touches the rod. Excess charge. Now the negative charge has a path to ground off the ball. Those two balls then become exactly positively charged. And that's the other thing too, is that positive charges don't go to ground. Negative charges go to ground because positive charges are protons and aren't going anywhere. So here we go. One more time.
Oh, that's so cool.
And we see the effect again.
This one touched it first. I noticed that
Yeah.
this time.
So, so that's the idea of charge induction. Objects that are electrically neutral, that behave as though they are charged in the presence of a charged object, or, as you're learning today as well, in the presence of a strong electric field of that polarity, right? Either a positive electric field or a negative electric field, and then the opposite charge will feel a force due to that field, either repulsive or attractive. So those are my demos on electrostatic forces, electrostatic interactions, and induced charge. So hopefully you'll watch this and hit that, bash that like button. I'm kidding. Get some merch. Anyway, sorry. So anyway, I hope that helps, and I'll see you soon with another vid, I'm sure. Thanks, guys.